Hi, this is Yinjin. I'm very excited to present our work on data citation today. Currently, in biological and medical domain, more and more scientific databases have been published online, which are curated by large communities. Those databases, unlike traditional publications, those databases are complex, structured, and fast-evolving. When the data in those databases are cited, we hope to give credit to the corresponding contributors by using some citations. Typical examples are Reacton, IUFR, and Eagle-Eye. So here is a question, that is, how should we generate proper citations for those data? Let's look at the state of the art in data citation. In terms of citations, we all know how to cite a paper or a journal. Those traditional citations are actually composed of snippets of information like author, title, etc. So in those scientific databases, the DBAs hope to mimic those traditional citations to give credit to the contributors. But it has been proven that the existing citations are not enough. This is because they only include the names of important persons like DBAs or PIs, which actually ignores other real contributors who did a lot of effort on curating the database. Besides, in our intuition, the citation should be different for different cited data that are actually retrieved by some queries. This is because the corresponding contributors might be different. Okay, what's the problem? What's up? Yeah, you are close.
Close the browser.
Yeah. Okay. So this problem actually comes from digital library domain. In that domain, a number of organizations have recognized the importance of data citation. They provide some principles and standards for that, which have been taken into consideration in our work. But we believe that data citation is a computational important problem, which will be justified using this example, the IUFR database. IUFR is a database which includes information about the drug targets on human body and the medicines that act on them. The drug targets in this database are organized into groups called families. Some families have detailed introduction page. Different families and different family pages are curated by different groups of contributors, which should be attached with some citation. Oh no, it happened again. Can you, yeah, so this browser, yeah, maybe I think you can stop connection. Maybe you can stop coding. Okay. Sorry for the delay. So let's look at a user case in IUFR database. This is a landing page for IUFR database online. There are a lot of links in this page, by which the user can navigate through this database and arrive at some specific page for some family, like this one, bioacid receptor. In this page, there are some citations. The first one is a fine-grained citation, which includes all the contributors for this specific family. Note that the query user to retrieve this family page is also included in this citation, like this one, the URL address. The second citation is a coarse-grained citation, which is a traditional journal citation to the entire database as a whole. Note that this kind of citation is the only citation provided by most of the other scientific databases. So as you can see, for some part of data that can be retrieved by some queries in IUFR database, there are two kinds of citations. One is a coarse-grained citation, while the other one is fine-grained citation. Both of them are hard-coded and manually specified by the DBAs. In practice, both of the two citations are used. But actually, there are some limits actually here because only the citations to limited number of the queries are provided, like the query to each individual family page. In the future, the DBAs hope that the citations to general user queries can be supported. But as you can see, the number of the general user queries can be infinite. It's impossible for us to manually specify the citations to every possible user query. So in this case, we need to figure out how to automate this process, which is actually a computational challenge. For this problem, we designed a model which is based on one concept called a citation view. A citation view is a triple which consists of view query, citation query, and a citation function. The view query is used to specify what portion of data to be cited. In this work, we only explore the case when the view queries are conjunctive queries and possibly parameterized. For example, for the family page that we have seen in the previous example, we can define the following two view queries over the family relation in the IFR database. The first one is parameterized by the family ID, while the other one is unparameterized. So let's look at the effect of the parameterized view and unparameterized views in data citation. This is a family relation from the IFR database, which includes the major information like family ID, family name, and family type for all the families. For the unparameterized views, V2, the instance includes all the family tuples, which should be attached with some coarse grain citation that can cite the entire family relation as a whole. On contrast, for the parameterized views V1, we can use different FID values from this relation to instantiate this view, so that each instantiated view represents one specific family tuple, which should be attached with some fine-grained citation. Such fine-grained citations should be different between different family tuples. The second component of the citation view is citation query, which defines snippets of information to be included in a citation. For example, for the view V1, we can attach such a citation query which returns all the contributors for each individual family page. The third component is called citation function, which defines the formats of the final citation. For example, the final citation can be JSON formatted citation. Suppose we can define a bunch of citation views here. Here the question, that is, how can we use the citation information from those citation views to automate the citation generation process for general user queries? One essential step here is to compare the definition of the views and the definition of the query because we want to make sure that the data mentioned by the view and the data mentioned by the query are related. This sounds very similar to query writing using view problem, right? But in fact, this research problem is different from query writing using view problem. Here is why. Suppose in IFR database, a user issues a query which returns all the GPCR drugs in this database. GPCR is a type here, so this query can be formalized as such data log query. After seeing this query result, the user might be only interested in one specific tuple in this query result. Note that not all the users are SQL experts. So in this case, they would like to manually select the tuples they want. In this case, we need to generate the citations for those select tuples, not for the entire query result. So as we can see, it's not enough to simply compare the schema of the query and the schema of the view to do the reasoning. So this goes beyond the query writing using view techniques. Let's look at our solution for this. So this is the architecture figure of our system. In our system, we will define some citation views. Actually, the DBAs will define some citation views and policies, which will be explained in the next few slides. For users, they will submit some queries, which will be executed against the database. At the same time, our system will take the user query and do some reasoning to figure out what citation views to be used for construction of the citation for the query result. Since we need to construct citations for every query tuple, the intuition behind the reasoning process is as follows. That is, we want to use those visible view tuples from the predefined citation views to construct the citations for the query result. Based on this intuition, we designed 3 approaches in which the amount of reasoning increases from the schema level to tuple level. The first approach is called schema level approach. This approach only reasons at the schema level and generates the citations for the entire query result. This approach is very similar to query writing using view techniques. However, in the other end of this spectrum, we designed another approach, that is tuple level approach. Somewhere in between, we designed one approach called a semi-schema level approach. Both tuple level approach and semi-schema level approach can generate citations at both tuple level and schema level. Due to time limit, I will only focus on tuple level approach here, but you can find the details for the other 2 approaches in our paper. So in the tuple level approach, the first step is to annotate the base relation tuples by using the view definition. Suppose here we have 2 views defined over family and family intro relation respectively. Both of the 2 views are parameterized by the family ID. So during the annotation step, we will instantiate those 2 views by using the FID values from those annotated tuples. More importantly, we want to capture the visibility of the view tuples early in the query result. So we will take care of the predicates in those view definition during the annotation step. For example, for the view V1, it has a predicate FID is smaller than or equal to 2. So in this case, we will only annotate the first 2 tuples in the family relation with the view V1. There are several possible ways to use those annotations to construct the citations for the query result. That is joint use, alternative use, and aggregated use. Let's look at joint use first. Suppose here the query which returns ID, type, and text of families with introduction page. So which can be formalized as a join query between family and family intro relation. In the query result, the annotations will be propagated from the base relations. For a certain query result, for a certain query tuple, like the first tuple, there are 2 annotations, which are from different base relations. In this case, in order to construct citations for that query tuple, we will jointly use the citations of the 2 annotations. There are many possible interpretations for the joint use. It depends on the policies from the DBS. But here, we can define joint use as join over the JSON object. This is very similar to natural join in SQL query. The second case is alternative user citation. Suppose we replace the second view with another view which is defined over family relation and unparameterized. Give me a query which is to return the ID and the type of the first family. The query result will only include one query tuple. For this query tuple, there are 2 annotations, which are both from one base relation, that is family relation. Here, we should alternatively use the citation information from those 2 annotations. Same as joint use, there are many possible interpretations for alternative use. Here, we can define alternative use as union, which is simply union the citations from the 2 annotations as a whole. The third case is aggregated user citation, which is used to deal with the case when users want to select more than one tuples. Suppose here, we only retain the first view, and here is the query which is to return the ID and the type of the first 3 families. In the query result, the user might select the 2 tuples. In this case, we need to aggregate the citation information from the 2 annotations to generate one citation as a whole. Let's go back to this architecture figure, and I will illustrate the citation generation process again. In the very beginning, the DBS will define some citation views and policies for alternative use, joint use, and aggregate use. For giving user query, our system will do some reasoning to generate the query result along with the annotations. For some tuples selected by the users, our system will generate such formatted citations by using the definition of the citation of use and policies. As you can imagine, our system should be, it's unreasonable for users to wait so long to get a citation, which indicates that our system should be an interactive tool. We measure the time performance on both synthetic scenarios and realistic scenarios in the experiments. The underlying database engine is PostgreSQL, and the system is deployed on a single Linux machine. Due to time limit, I will only introduce a performance result on realistic queries against the IUFA database. Those realistic queries are from the owner of the IUFA database. In this experiment, we measure the total execution time for reasoning the fine-grained citation by applying the tuple-level approach. As you can see, for all of those queries, it only takes sub-seconds for tuple-level approach to finish the entire reasoning process. Some of those queries are very complicated. For example, the first query is a join between 3 relations, which can generate more than 8,000 tuples. It implies that our approaches should be very efficient in practice. Just to conclude, in this work, we explore solutions to automating fine-grained citation generation process for general user queries. In the future, we will explore the connections between our work and the data problems. Since, as you can see, the annotations in the tuple-level approach are very similar to problem tokens. Furthermore, we will think about how to enable bibliometrics, like H-index for curators. Besides, we will think about how to support versioning database in the future. That's all. Thanks.
So I have a quick question.
Okay.
I have a quick question. So I guess you sort of said that versioning is for future work, but
Yeah.
you assume that each sort of row has like a single citation or a single curator. And so if there were multiple curators or a timeline of curators, can you tell us a little bit about how your system could handle that?
You mean?
If there are multiple edits on a single row, and say there are multiple curators, for example.
Yes. So actually, our current work can handle that case. This is because for each tuple, it can be curated by multiple curators. So you see, since our work, we just assume that the citation are JSON formatted citation. So you see, so here there can be multiple contributors here actually. So it's possible to handle that case. Yeah.
Okay, thank you very much.
Okay.